act as a very valuable library.
It's beneath here, beneath your neck here.
Okay, so this.
Yes.
So, actually, when we learn about the theory, if you want to do any serious computations, you need to go back to either calculators, tools, or there's a whole bunch, also possible. So, I will also mention some about that on the second lecture. But the first lecture, I would like to kind of survey and kind of more introductory to understand the structure of conical transition. We really understand so far. So the topic is quantum extremal transitions. And this is the first talk. And I'll explain it for and even though in a lot of situations it can extend to other people, but let's focus on that. It's a joint work with YPD, quite a long time ago. Mainly, I will base on this paper, and so it's just you have partial integral, and you contract it into another partial integral, which is singular, and suppose we get some finite number of ordinary double points. So you know that, and suppose you can smooth this singularity to another partial integral, and we call this process a transition. So here xy are SU3 partial integrals. Okay. And we'll work only in projective cases of complex numbers. And if you look at the local structure of this, what you get is all the singular points you just get some 3 speed. And if you take this look at this, it's just contract some rational curves to a singular point. So it's a very easy topological surgery local at each point. But we are really working on the global geometry. So there are quite non-trivial relations between these relative cycles. And so the local structure, of course, can be understood quite easily. Is the neighborhood is basically just the contiguous bundle of it, and the neighborhood of this is even more familiar. It's just there's normal bundles, just minus 1. But what's the non-trivial condition for that? Is you have many you have k cycles here, and you also have a k rational curves here, but they are not independent. They are relations of that. So let's write down the topological constraint. So let's say mu defined to be h21x minus h21y. So the picture is the following. So you have moduli space of your capital Y. And when you do the contraction will extend to the whole family. So the whole moduli space will be embedded into the boundary component of the moduli space of S bar. And the moduli space of S bar is actually the same as the moduli space of X if you do a computation. And one, which means you should have row relations. And conversely, even though you have k rational curves, but you only have a row linearly independent one, which means you have mu relations between them. So let's just write out what's that? So the relation matrix. There's a, let's call A. There's a matrix. And B is another matrix. A equals 0. That's a relation. C1 is for S1. These are all the curve E1 and this simple notation. Okay, later on I will write this in more detail, but just say you have a matrix, relation matrix. Okay, so before I talk about the detail, I want to study as the professor also knows, once you have Calabi-Yau, we have two topological theory on that. One is the A model, one is the B model. The A model is about homogeneous theory. The B model is about the variation of structures. And then we want to understand how they behave under such a transition. But before I go to that, let's recall the definition of extremal transition due to Darling Wilson. You actually have three types. Let's go 1, 2, 3. And the type 1 is the math side actually contract curves to points. And that the canonical transition, of course, is type 1. Those are to be the simplest possible type 1. And for type 2, is we contract a divisor to a point. And type 3 is we contract a divisor E to a curve C. And in all the three cases, what we know is the following. You can do a symplectic deformation. Okay. What does that mean? Which means near the exceptional locus, you do some holomorphic deformation, truly holomorphic deformation. And outside, you just take identity. then you use partition unit to do it together, and within in the same tamed by the same symplectic or Taylor form. And if you do that, we call it symplectic. And then you can simplify the structure of the sectional set. And in the first case, you just get conical transition, as I just described. So those pi, so you get ODP. And for the second case, you will get this E is actually a smooth Delpedal surface of degree D. And we know that they are all completely classified. And today I will just talk about the first one. But we have another two talks on Wednesday by Chin-Lung Wang and Chin-Lung Wang. And they will talk about the type 2, the recent progress on type 2. And for type 3, Wilson actually proved these curves, C, must be smooth. And after you do a symplectic deformation, you will get E to C. You basically can assume this is a conic bundle. I will call this 1 plus. 1 plus means 1 including this case. And you have the true type 2 case. And you have the 3, the type 3, but now the type 3, I should say this is type 3 with genus 0. Okay, that's after the perturbation, you have 3 types. And this is something still quite hard, we are still working on. Okay, so we are in the first case. So, in order to study the detailed geometry, we need to do the so-called semi-stable reduction on both maps. So here you have a contraction. Then you can do the deformation to normal cone with the sectional locus. So what you get is Y is a general fiber, and the deformation to normal cone will split into Y tilde. I will write down what's that, and the intersection will be ER. And here the other component will be EI tilde, which is the local model. Okay, so you have Y, and you have a lot of Manson curve. And the local model for each Manson curve is just a computation of normal boundary. and you have a lot of it of them, so just get that. So this is usually called deformation to normal form. And for your original complex degeneration, then we need to do a semi-stable reduction. So in this case, you get your general fiber is X. And your spatial fiber is looks very similar. You still get this EI. Here, this is your local model, and this EI is precisely the P1 times P1, which can be regarded as the infinity section of this local model. And it's easier to look at this picture because here the local model of this X at a singular point. What's the semi-stable degeneration? You start with your family. Let's take out a one-dimensional family like this. And the central fiber is your X bar. Okay, that's the picture. And the singularity, local singularity, we know, is something like xi squared equals 0. So the deformation family, you write this as T. It looks like this. But in order to do a semi-stable reduction, you need to raise this to power 2. So usually we will call this a degree 2 phase change. And when you actually do degree 2 phase change, you just blow up the total space at a point. But once you do that, the normal bundle is a quadratic triangle. So that's a cube. So this is quadratic triangle. And in this way, the here is just this fiber is still YQ dot. YQ dot is the blow up along all the PI of the S bar, which is after you do the degree 2 phase change. And then of course we know once you blow up all the data point, then you will get this is P1 times P1. Okay, so if you compare with these two pictures, then a very good thing is about it. So you want to study the relation between X and Y. But after you do the blow up, here you do a semi-stable reduction, here you do the deformation to normal form. And you get exactly the same YQ dot, which is the blow up of this. But no matter what it is, it's the same. And then the difference is this is the local model of X. And this is the local model of Y along each decision models. So once you type of degeneration, they are all so-called double point degenerations. Okay, which means at each singular locus, you only have two divisors in the set with each other. And once you are in that situation, you can apply in Gomo-Witten, you can apply Chin-Lung's degeneration formula. And in B model, it is of course easier. You can apply this Clemens Schmidt this equals or the variation of Hart structure. I mean, B model you can do the much more general situation. You can do any normal procedure. Right? But for A model, the best we know today is still for classical quantum. Okay, so that's a real we can do canonical transition. And if you work out this, work out the degeneration analysis. And what you will get in the B side, I mean variation Hart structure. Then you will get a picture. So H30 infinity. Usually people sometimes right, as a limited part structure at a point zero. So this is quite confusing. Sometimes you want to write this, sometimes you want to write this, sometimes you want to write this. But you all mean the same thing. Because in your coordinate, you actually you want to look at the t equals 0. But if you really calculate the variation of part structure, you need to lift this to upper half plane. And then you are looking at the infinity. So maybe a better notation is used on limit. But anyway, you know, no matter what I wrote, I mean this. Okay? But you look at that. So you look at the middle dimensional cohomology, and you have 2, 1. Here, 1, 2. You have 0, 3. So the middle cohomology will be separate, split into a mixed Hodge diamond, and the structure is you have something here, it's 2, 2, S3, and you have 1, 1. I just noticed my place is different from your convention. You actually switch this, but I do it in this way. Okay, so what happens is this place. Your original H30 is just one dimension because you are in Calabi 3. But now this piece was still kept in this place. This is because of the finite distance condition, which simply means the monodromy operator will annihilate this holomorphic spherical. And this is basically spanned by your spherical. So once you keep it fixed, this one-dimensional piece stays here. But this is your modular space, originally lived in the H21 cohomology. And this guy has some piece split into this part. And dually, some piece of this part split downstate. Okay? So this is the whole mixed Hodge diamond. And for the other part, you just get 0. Simply because the splitting of this strip has to be all coming from this part. But you fix this part, so all the other parts should be 0. And then your monodromy operator is going down in this way. So you go down here, and because of the Hodge duality, you get an isomorphism. Yeah, and you see all the other groups, they are all invariant under mode. By your original monodromy operator. By the way, you have this Hodge diamond. And you do some calculation. I mean, in order to get this picture, you will figure out this is exactly isomorphic to the space of vanishing cycles. That means the span by this SI. And so you have a dimension mu. And this is naturally identified to be the dual space of the vanishing cycle. Moreover, the horizontal piece. So you look at the kernel, then because everything here, the 5 terms, they are annihilated by monodromy, total monodromy. And if you take away H3Y, because this part, these three, they just correspond to the together. This gives you the original Hart structure of Y. So you get this identification. To summarize this together, then you get the so-called basic this sequence. Which reads as we write h2 y divided by h2x, and goes to the rest sum I from 1 to k, and h2 of EI. Remember, EI are quadratic circuits. The essential divisor appear in the intersection. P1 cross P1. And then you quotient by h2 qi. And qi are quadratic circle. So by Lefschetz hyperparameter, we know this is rank 1. So for each piece, you just get one C. Because this is C2, this is C. And then you mark to the vanishing cycle space. And the good part is we really know what's the map. So here, you just apply the matrix B. And here, you just apply the matrix A to the transpose. Okay. So AB are the relation matrix. But the interesting thing is, you take we call this excess A. And we call this excess B. Excess A from Y. And this is excess B from X. And this is dimension mu. And this is this dimension rho. It's relative to car. And but then you apply this B matrix. Remember, B is the relation of this cycles here. And while A is the relation matrix of the curves here. But work out the meaning of that relation, you will get this in this sequence. And of course, there's some lengthy, quite elementary work after you work out this invariance analysis. I could Clemens, G in this sequence. After you do that, then you will conclude this. And you can view this as a Hart accelerated version of the original K equal mu plus 1 and rho plus 1. Okay. So you upgrade this numerical identity to Hart series. You observe this is the Hart series here is weight 2, and here is weight 2. But B is originally the vanishing cycle, so it's weight 3. So it looks like inconsistent. But if you look at this limiting Hart structure, this really comes from B. So it's so you see, from here, we know B is actually kernel of A transpose. And A, of course, A is also kernel of B transpose. Or we compose together A transpose B. Okay, so our goal is not just this. This is just vector space. So we want to do a quantum or D-module aspect. So we really want to put integrable connections here. So for here, you want to put the Brownian connection, which calculates the over variables. And here, of course, you want to put the Gauss-Lambda connection, which calculates the variation Hart structure. What's here? Here, you get a space. CK. Okay, so I will explain this. Okay. So we have this picture. I usually prefer to write this or write this to denote a transition. Okay, so this means a contraction smoothing, and this is a degeneration and frequent resolution. But in this situation, we know from here, we know the A model of X is strictly less than A model of Y. Let's write this this way. Okay? And conversely, the B model of X is strictly dominant the B model of Y. Okay? But this is easy. Because we just explained the B model of Y, so A model is formal region. Oh, quantum cohomology. Well, if you just talk about genus theory. And B model is variation hot structure. And we just say the B model of Y is totally controlled by the monodromy invariant part. Yeah, so yes, of course, yeah, you need to take away. So the excess one. So yeah, so if you take away the vanishing cycle part, then you exactly achieve this B model of Y. So this part is okay. But how about this part? So let's separate the discussion into two sides. So the goal is to determine both the A model and B model on the same X by the A model of Y and B model of Y, and vice versa. Okay, so you see, so my B model is larger than your B model. But my A model is smaller than you because you contain more rational curves. I don't have those curves. Those curves are contracted. But then I want to have somehow a mathematical theory to make sure all the topological field theory invariants still remains. And this could be determined by each other under transition. Okay, that's the goal. I mean, in another way to say it, even though it's not quite formal, it's maybe not that good, but I still want to say it in this way. So if you believe string theory is unique, then you need to mathematically consider something like this. So the quantum data on X, the total quantum data should have the ability to decide the quantum data on Y after the transition and conversely. Okay, so we have to answer this question. So the first direction, let's work on. Of course, when you mark down, you will go to X bar, and you devote to X. But here, in this case, it's quite easy to prove the class, every class are invariant cycle. So the class pushed down to beta here is also a class. It's not hard to be identified. So this formula actually makes sense. And even this very simple looking formula actually was first observed by Professor Hosmer, I guess. in HK Ty manifold. I guess that is some calculation of examples. But anyway, that's the first theories I know. I was a student at that time. But the reverse proof was wrong around 2000 when they proved the degeneration formula in symplectic paper. And then Jun-Li around the same time in H-break. This is H-break. This is symplectic. But usually people have difficulty to follow this approach. So if you look at this, it's completely H-break geometry. And then to really carry out in this specific, Jun-Li, it doesn't work on this transition. He just proved the degeneration formula. But to carry out this formula is done by Liu Jianhao and Yao. It's another postdoc of Yao. So it's one. So anyway, we have this formula. And this formula can be proved using degeneration formula for Cardiac Schriefel. And but it's very good, as Lee says that this is completely dominated by this. Because the global invariance of X is completely dominated by. Okay, that's very good. But then the problem is I also need to decide, and I also need to determine the B model of X. So the problem is how to get the B model of X from AX from B1. Okay, then what's the question here? So let's go back to this modular picture. So you have this B model, which are categorized by variation Hart structure, a modular space of Y. And as I said, it just corresponds to a co-dimension mu boundary strata here. So you control some variation Hart structure only in the boundary slice, like this. But the thing you want to reconstruct is the go outside this boundary slice. Then how can you do that? You don't have any other information on the B model. So the only thing you have more than X. No. The only thing you have more or less is the A model of Y. So the A model of Y is globally on Y. So essentially the difference is those rational curves. You contract. So how can that be possible to do such a thing? Okay, there are 4 steps. So the first one, we need to set up the coordinates. In order to do any computation, I need to set up the coordinates. This is basically due to freedom. In the following way. So now I have to write down the matrix A, which is A1 with A mu. Or it's Aij, which is a matrix, which is K times mu matrix. And for any P in CK, for any of the rational curves. And turns out this gives rise to the partial smoothing of OPI with ARI on 0. So this is vector, this is vector. And just look at the ith entry. That entry corresponds to whether you pick up the point PI. And the coefficient is non-zero. So that will give you a smoothing, partial smoothing will smooth this ordered point. Okay, so in usual way, how people apply this is you need to find a totally non-trivial relation vector. Now, so you mean all the relation, all the curves you contracted need to satisfy some relation, and all the coefficients has to be non-zero. In that case, you can find the smoothing simultaneously smooth out all the points. Okay, that's the usual criteria of agreement. But let's just do it for any direction t. Okay, put it this way. And then we also define the linear function ARI, which is just you expand this up. Okay. I just write down that coefficient. So I get this linear function. And it defines a hyperplane. I will call it DI inside the space C mu. And I. Okay, so what I'm doing is you look at the locus you want to analyze. Suppose this is point S bar. And you look at the moduli space near S bar. Then what's the structure here? It looks like a product. And the moduli space locally will look like the moduli near S bar is locally over the bone. And that's called the parameter coordinated to be T and S. So T is the coordinate in the transversal unidimensional slice. So that's a real I define this dividing in this transversal direction. And my is a general modular of y. So the parameter is just S. Okay, so what you see is the discriminant locus is actually quite, it's not just like this. So how I wrote is the strata when you take the contraction. But if you look at the moduli space here, MS bar, then in order to get this strata, that's actually cut out by many hyperplane. Those hyperplane was described by this DI. Because if you have any DI equals 0, then that point will not be smoothed out. So the only way to smooth out all the points is you need to avoid all the hyperplanes. So, but you have, how many hyperplanes you have? You have a K. You have a K hyperplane. But it's just inside a mu-dimensional space. It's a strictly I'm drawing the discriminant locus. And these are the D1, D2, etc. The D mu. And this axis is exactly my. And we give this a name. We call this central hyperplane arrangement with axis and y. But anyway, what I want to tell you is, it's a good thing. It looks quite nice. You just you just cut this strata by many devices. But one thing is bad is it is strictly not simple normal crossing. Yeah, because even if you just look at the case mu equal 2, but the k is strictly larger than 2, so at least you have 3 lines. So you are not in the simple normal crossing situation. So that tells you the standard hard theory, like variation hard structure theory of Schmidt, you could not be applied directly in this situation. So to really analyze it, we need to prove something. We need to generalize something in Schmidt theory. Okay, so let's look at that part. So that's the first step. You set up the coordinates. The second step is you need to look at the transversal direction. Which simply means those mu transversal direction. And we have the important opposition, which is the Picard-Lepschitz formula, which says that we choose our holomorphic 3 form, Ts. Ts are the coordinates we just set up. So for Calabi-Yau 3 form, we have 3 form. Now we take the family of 3 form on the whole Ts family. We pick up this and symplectic basis I will denote by alpha 0, alpha 1 to alpha mu, and then alpha mu plus 1 to alpha H21. So this is the first half. And then this corresponds to H3 0, and this corresponds to H21. And then you have H12, and let's denote that by beta 0. Okay, actually, okay. Okay. Beta 1 to beta H21, and then beta 0, including more symmetric. By the way, that's a symplectic basis. Such that, and for the first mu, usually we call this A cycle. We do this kind of thing. But let's denote this by gamma 1. And this is gamma mu. Because I really want to mean these are validity cycles. And the basis of validity cycle, because we know you have actually total number of k speakers, but you only have mu independent of 1. So let's put it up here. Such that that's the most important form. Omega, the holomorphic 3 form, pick it up like this as an expansion A0x plus summation j from 1 to mu and gamma j star tj and plus something holomorphic or higher order term. That's it. It's higher order term. And so pi I, then Wi, and log Wi, and Poincare due of the speed. Oh, that's the most important character. So, okay, when you do anything in Calabi Algebra, of course, no, the most important thing is to calculate this. To get the formula to express your holomorphic circle. If you can do that, then you can do integration of this cycle, then you get pure integral, then you can calculate the calculus equation. So now the important thing is I want to analyze what happened in the transition boundary. So I need to know. You see, I define these linear functions, which define the discriminant locus. And then this formula, if you really have a normal crossing device, then this formula is well known. This is just the classical standard evaluation formula. But the problem is you don't. Now you have more linear functions. Your discriminant locus is a central hyperplane arrangement. So it's a priori quite unsure. These are not coordinates. These are linear functions built on coordinate Ti. But still, I claim you have presented. Okay, that's actually the main result. One of the main results of that paper. So once you have that, and notice that okay, you can derive the following corollary. So of the prime prefix, cubic, or in physics literature, it's called corollary. All you have to do is just do differentiation on this and integrate it partly into the usual definition. What's in corollary? It's basically, there are several definitions. Some definitions is this. Yeah. So you take the 3 derivative, integrate with it again. And this is called corollary. And then you get, so let's denote UPPS to be integration of your holomorphic form along the B cycle, the B cycle. So P, then from 1 to mu. So you just define this same thing. Then we differentiate this function U P and N. Okay. Okay. The one thing I need to say is this notation UP is really not UP. It's really a function. You really have a function P, and take a differentiation in the P direction. You get this. But that belongs to part of Calabi theory. But it's a magic. Is you really know this is once you set up this coordinate. Yeah, you really know that, that's called the pre-potential function. And in Golomb, we cannot correspond to the homomorphic potential. So anyway, once you set up this, then the triple intersection will give you the Picard coupling you want to take. And that's given by higher order term plus 1 over 2 pi and sum 1, 2. Okay. And you get some pole that will ride along the discriminant locus. Along all the discriminant locus, you have a pole. And the coefficient is AIP, then AIN, and AIN. That's the result. So that means your Picard coupling has a logarithmic graph along all of these discriminant locus. that gives us some confidence. So because what I want to do is, I want to say, I want to use the A model of Y to give you the B information on X. So I already tell you, using the relation matrix, you can produce at least the asymptotic term. Which means, original picture of the moduli space, I just erased it. You have no idea. And you contract. You have this. You want to reconstruct this. So now I just tell you, at least you know some infinitesimal notion. I didn't tell you the exact one. I just say at least you can control the pole behavior. The coefficients are controlled by the relation matrix of the contracted curves. Okay, so that's a set. So you can have a simple question. Probably a very nice question.
Can I have some Jordan form of this in important matrix over there? Variation, what's this? Right? Yeah. So you wrote the important action in monodromy action.
Oh.
And I just want to connect this monodromy action to the expansion of the integral.
Yeah.
So can you give me the form of the monodromy action around the contour?
Yeah, of course. I think okay. Okay, good. That's exactly the reason why I can prove this. Okay, so okay. I plan to talk about that later, but since you asked, I will give you the answer now. Okay, so what is it?
Maybe another way to ask is how's the dual cycle? So over here.
Under the period. Under the dual cycle just means the dual cycle under the symplectic period.
Yeah. So you showed us the vanishing cycle gamma 1 to gamma mu.
Yeah.
And then how's the dual cycle?
You mean this one?
Yeah.
Yeah, that's exactly why I wrote it. The gamma star J is something here. It's a dual cycle. And here is the vanishing cycle.
Vanishing cycle. And over here.
And over here, this is the dual cycle.
Right. And then vanishing cycle.
No, this is the dual vanishing cycle.
Yeah, vanishing cycle.
Yes. So this is vanishing cycle.
Yeah.
Then I take dual, I get dual vanishing cycle.
Okay. For the vanishing cycle, I think yeah, probably it's related to what you said, the Picard vector theory. So standard Picard vector theory, vanishing cycle appears together with dual cycle.
Yeah, that depends on you use homology cycle or cohomology cycle. So what I wrote here is really homology. I really wrote let's check. I really mean sorry. I mean okay. I know what. So I have to check. I guess I'm actually using the homology cycle. Sorry. Yeah, sorry. I use H3. I use homology cycle. Yeah. That's the reason I want to put comparative. No, then that's okay. So this is cohomology cycle. And okay, good. So this is homology cycle. And this is the comparative cycle. Okay. I'm sorry I say it's wrong, sorry. Maybe not wrong. But anyway, this is correct.
So I also have a question. So is your omega 30 form? Omega TSI 30 form. So
Is that 30 form?
So how come Untitled is also Untitled SI is also?
No. It's a 30 form. That's correct. union of the rational terms. We consider it deforms the complex structure, but only on open Zariski open state. And we call this the linked B model. So see, the terminology is if I deform the complex structure of the whole Y, that's the original B model. But if I want to take care of the information of C, the better way is like just remove it. I deform the remaining part. Okay, and let's use an notation. P is the union of Pi. And 1 to K, this is point. This is cycle in S bar. Okay. If you do that, you will get your original deformation theory, which is controlled by H1 of the tangent shift. That will embed into the deformation theory of the open part, of course. But the problem is this one will be isomorphic to the, but you need some singularity theory to prove it. Basically, you need to use this is an isolated singularity and very good. It's a conical point. Actually, this works more generally for isolated Gorenstan singularities, studied by Stingray. It's basically Schiller. And you have this. You need to do some local algebra computation to realize this isomorphism. Okay. But if you look at it, let's just the deformation space. They want to do this, really integrate this deformation. And locally, we have My is a spec R quotient by P1 to P mu. R is okay, and this is embedded in S, which is defined to be spec of R quotient by P1 to P mu by the Taylor square. Okay. And this is embedded into MS bar, which is spec R. That's my definition of R. So I just write a local picture, local coding. I call it spec R. And if you mark out all the defining equation, then of course you get Y. But if you look at this deformation, then something interesting happens. This is a Artinian speed. So as a scheme, as a set, it's completely the same as your My. But it encodes the infinitesimal direction, the first order direction. And the result is Ts, which is H1 U Pu is integral in H1 E1. So you have a bigger space, which is this one. And if you restrict to this subspace, then of course you will go back to the moduli of Y, and you will have the Bogomolov total theorem. So this unobstructed. So if you restrict to this subspace, it's unobstructed. But you get the modular space. However, it's obstructed in other directions. And of course you know that because otherwise to a compact dual. That's just usual notation. This compact dual of pure domain of the pure. And then this is horizontal. And this implies you get psi, which is from M to D. And this is basically MS bar. It's this simple. It just means I want to look at neighborhood of your modular space. So what I'm doing here is I want to go from here outside. I want to determine the modular. But I use this over an Archimedes thing. I created this tangent direction. And once I created this tangent direction, I apply to Frank Griffiths. I get the maxima integrable slice. So I reconstruct the modular space. So that's it. But if you look at it carefully, it's not yet finished. Because this is in the compact dual. But in the half theory, we cannot map the compact dual. We need to map the original one. The compact dual means you lost the polarization condition. So you need to go back to the original pure domain. And the last step is exactly how I prove this declaration formula. Actually, I reversed the logic of everything. Because what I really need to tell you is the statement I'm going to write down now. That's actually the first statement you need to prove before you can write down anything I wrote in the last 20 minutes. So that's the bottom of this here. So the bottom of this here. What's that? Which says that your original variation hash structure. That's your original variation hash structure. The pure map. And we know you always write something like this. This is horizontal. And this is your original variation hash structure. So what's the neighborhood of this theorem? You have your original theorem map E from your modular space to your domain, which is horizontal. But you want to understand the structure after you do complementation. Then what you do is you twist this monodromy action to this side. And what you need to prove is, after you twist this monodromy logarithm part, you get something extendable to the degenerate bipolar. So you get this thing to be horizontal. Okay, but that theory only works for normal coarsen case. I spent like I don't know, Chin-Lung Wang. He was my PhD student at that time. I guess during your whole PhD study, I was trying to prove this. I always say I want to prove this, but I don't know how to prove it until maybe before you graduate. Okay, let me tell you why this is hard. Because almost everyone, including myself, try to reduce this to the original neighborhood of this mean. Because you just take the resolution. You just have hyperplane arrangement. It's very easy. You just blow it up. 'They will get a lot of pieces. this, you need this NI NJ to continue. And this is true if you are in normal closing case. But once you are not in that case, you take the fundamental group, you already know this is not really. You never had this. And so the theory I proved or in our paper is, I proved this holds for central hyperplane arrangement as long as you have this monotony commutativity. So that's the condition. So, the really need is condition. And once you have that, then you can copy the proof of Schmidt. Actually, I just copied his proof line by line. Then how he used the Hartle extension, how he do this dimension reduction. But anyway, I copied it. Then I found that's the only condition I need. Then so I generalized this total obvious theory to this state. And that's just what I show you is from this Katz Oda theory, we can construct this first, which is a holomorphic horizontal map. Then we already know the monodromy because by Picard-Lattice formula. And because of the Picard-Lattice formula, the simple Picard, we know this commutativity. So then I can form this. And even though you have a lot of linear equations here, but still, you get this and multiply by this, then you get and notice that, as I said, where you use this relation matrix, that's encoded in this monodromy operator. So the action actually was controlled. So this was actually controlled by relation matrix. Okay. So that's the story from that end of the story. You want to get you group from x to y, y to x. So the ay determine x, ax, this is easy. Like the simple formula summation formula. But in order to get bx, you really need your by and your ay in some twisted way. That's a stopping notation. I use this notation to mean I want to twist this vanishing speed in the way I just described. Okay, but of course, okay, this looks good in the theoretic sense. But if you are really you really want to challenge me, probably is if I give you one example, can you really take your guess? That is always our problem in mathematics. So when you say, for example, when you write down any group like this, I don't know. We learned a lot of formal things like that. But if you really want to what Starship always said and tell you to calculate this whole margin, I don't know. I don't know if we really have any method beyond take an open cover and compute check or margin. But anyway, so forget about that part. We finish one direction. So now let's move. I only have less than 10 minutes. So I want to tell you the other side. So the other side is x to y. Okay, in one part is trivial. Because the by is completely included by bx, we just explain as the monodromy invariant part. Yeah, I just erased those down. Please touch diagram. But here it is. So you have a variation half structure. You want to decide this part. You just take a monodromy invariant part, basically. So you just get the system. You get the system, and that's the variation half structure. So in one direction is almost. P bar 0 plus S epsilon P bar epsilon and plus S C and T bar C and plus S0 T bar 0. Notice the index some are upper, some are lower. Okay, and this is a general element in Hx, and which is embedded in Hy by a canonical injection. I want to compute formal return. So here I only restrict myself to even cohomology. And you have a including, because in this case every cycle is an invariant cycle, so even part. Okay, so that's the coordinate on the downstate. And so I write a general element U, which is some L from 1 to rho. That's a relative Picard. And I create a new variable UL, PL. Here I have a bar, which means the class are from downstairs. And here I have no bar, which means that the new class is on 1. So this is P1 to P rho. These are bases of the relative Picard, y over S1. So let's set out the coordinate like that. And also we get the dual class P1 and P2. Then the formal written potential is F genus 0 Y, and the P, the variable P is now written as plus U. This is from X, this is from extension, the additional one. And yeah. So for Y, you have a contraction, the transition to X. Your Taylor comb of X is embedded in Taylor comb of Y as a codimension rho phase. Yeah, because you have you just pull back your Taylor comb. So you just now you have some boundary phase of codimension rho. And may choose. That's a tricky part, but that can be done. You can choose your basis such that the relation matrix BIL, this is the relation matrix of your vanity cycle. But you choose your class on Y so that this is the intersection number CIPL. That's the interesting part. It's not hard to prove, but you need to go through a lot of topological calculations. So the relation matrix, this is part of the basic in this sequence. So the relation matrix on this vanity cycles, SI3, can be realized as some intersection number on the Y side. It's a topological statement. And we also denote this very simple function to be sum of D in N. It's a very trivial geometry series, which is Q divided by L minus Q. Let's define it this way. And you know what I want to do. I don't want to write down the multiple cover formula for the -1 curve. So the proposition here is multiple cover formula. Or we call cover formula. But now it's on the A side, on the Y. Previously I wrote on the B side of X, but now I'm on the A side. So it's we call calculating, I mean the 3-point function, which is defined to be the L of M and the triple derivative of your genus 0 potential I P. Okay, so this just corresponds to, you can determine the asymptotic part by the relation matrix of your B model. Okay, so just similar to what I said before. But this is not enough. Because you just determine you can't calculate the block behavior. We don't have the thing I described here, the so-called parameters, context structure, the total OBC regeneration, because we are not on A model. So I don't have this the remaining step. So to finish this lecture, I just tell you what's the solution to the problem written in our paper in a very unsatisfactory way. Now that's the best thing we can do at that time and also today. Unfortunately, even after so many years. So the thing is the so-called linked A model. We just do the same thing. So we know this formula. I just wrote it down before. So we use this formula to say global return of y trivially determine global return of x. But now what we want is the converse. What we want is, if you know this, how can you decide the individual terms? So the trouble is how to determine each term. How can you do that? And then the second is you study global return. Actually, it's not global return because we don't have global return on that. You study global return on the space y, the space of x. So previously you study the formation of y, you remove those rational curves. Now you study your counting function, your counting invariant, but you remove all those energy cycles. Of course, this is open space. So let's call this n. So what does that mean? So you want to study your global return counting, but you are not allowed to touch the energy cycle. And if you do that, then you will figure out topologically, we actually have n is homomorphic to y. Remove this rational curves. Because you when you remove variance cycle, it's the same as you go to y. It's a surgery picture. But this is 2-dimensional. And this is real 2-dimensional. So that means if you consider the second homology, that will be exactly the same as the second homology for y. So that means when you consider a class here, it's the same as consider a curved class here. So now you can just, once you can define this invariant, then of course, what you get is the global return, the linking invariant. I will not call this formula. I just call this linking invariant with the class gamma. It's the same as the linking invariant of class gamma, but you change the symbol x to y. So, but the meaning of these two are different. Because the gamma here is really a curved class of y. But gamma here is a class in second homology of n. And the invariant really means a global return which does not touch the valence cycle. And this can be proved. The existence was proved again by Chinese degeneration formula, but in cycle form. Not the original numerical form. That's another. You really need to work out the cycle decomposition, and then you can divide this. And that's the way we finish this part. Okay, but then you can ask the even more serious question. Do you really know how to calculate this? So actually, I gave this statement. The first time I gave this is in is in